All right, everyone, I'd like to welcome you to RMU. My name is Tony Kurzman. I am the co-director of the School of Engineering, Mathematics, and Science Research and Outreach Center. That's a mouthful. That acronym is a mouthful, too, SEMS-ROC. But anyway, we're really excited that you're here. We want to thank NAYGN for contacting us and helping us to plan this, for allowing us to host the event. And welcome NAYGN members and RMU students. I see a few of you back there. So we're excited to learn about some of the nuclear reactor technology, and I think I'll leave the rest to Paul. The one last thing, please silence your cell phones, and I'll leave the rest to Paul, president of NAYGN Rolls-Royce chapter.
All right, everyone, thank you for being here. Like Tony said, we appreciate you guys coming. We think this is going to be a great opportunity to learn about the new technologies in nuclear, and specifically NuScale power. So one thing you may have heard Tony said was NAYGN. So for you RMU students and maybe some of the other people in the audience, what the heck does that mean? It stands for North America Young Generation in Nuclear. So it's an organization that was formed in 1999 by 7 young engineers with a focus on promoting nuclear power, retaining good talent in nuclear, providing an opportunity for knowledge transfer between the generations, a good networking, social opportunity, and professional development. So all of those pillars of NAYGN are kind of being checked today by this lecture. So it's a good opportunity to check all those. So if you might be meeting some new people, coming out to a social event, things along those lines. So all those are good things for us to professionally develop as engineers and students. So thank you all for being here again. One thing I wanted to also note is Rolls-Royce. It's not just cars, not just jet engines, it's also nuclear. And we're in the area. We're less than 5 minutes from Robert Morris. So we're in the airport office park. We have about 200 employees at that location, and we have employees around the country and internationally too. So we have a big influence in the nuclear market. So if you're a student, you're looking for a job or a potential opportunity, we're right here, right in the area, and we're a good place to start. The next thing I wanted to do is introduce our speaker, Nils, and read a quick bio about what he's done in the industry and what he's doing now. So Nils has been in the industry for 40 years. He began his career supporting the construction of Palo Verde Nuclear Generating Station, which is in Arizona. Is that correct? In the late 1970s, before joining combustion engineering and their methods development group. The majority of his career has been with Westinghouse, where he directed various technical organizations, including engineering, supply chain, and nuclear fuel manufacturing. In 2000, Nils began the business development phase of his career. At various times, he has led new plant business development activities in the US, Europe, South Africa, and Southeast Asia for both large and small modular reactors. Currently, Nils is in the regional sales manager for NuScale Power's SMR business with focus on the domestic market. Nils has a bachelor's and master's degree in nuclear engineering from the University of Arizona and lives in Wesley Chapel, North Carolina. So I'd like to welcome Neil to the stage.
Thank you. Can everybody hear me?
Sure.
Not sure how well this is working. But I want to thank Robert Morris University for hosting this. Thank Rolls-Royce for inviting me to speak. Today I'll speak about the NuScale small modular reactor. The NuScale small modular reactor is an advanced reactor from the Department of Energy perspective, but not really an advanced reactor from a technology perspective. We're not heavy metal, we're not fluoride salts or chloride salts, we're not HTGR, we're a light water reactor. And that was done on purpose. Light water reactor technology has been around a long time. There are millions of years of operating experience. There's licensing structures to be able to license a reactor. So NuScale Power felt that the best way to bring SMR technology to the marketplace was to start with something that was reasonably familiar. Now, from the Department of Energy standpoint, this has been good for them and good for us. So we were the recipients of a grant. Well, not really a grant, it's a public-private partnership between the Department of Energy and NuScale on a 50-50 cost share basis. $215 million over a 5-year period. Fiscal year 2018 will be the last year of that 5 years. So some of the work that's been done has been done with the support of the Department of Energy. They've considered us an advanced reactor because it allows us to fit under some of their programs, which has been good for them. They get results and we've got results. So let's start a little bit with the global energy reality. So where are we around the globe? So clean water, clean air, ability to transport necessities. So how do you get food and medicine in places? Well, you need energy to be able to do that. And basic electricity. What's the availability of affordable, reliable electricity around the world? I mean, those are key things that we need to be delivering around the world. This is an energy economy. So, from a NuScale perspective, so in 2007, NuScale Power is formed. NuScale Power is formed based on work performed at Oregon State University for the multi-application small light water reactor program from the Department of Defense. Jose Reyes, our Chief Technology Officer, participated in that program, and that developed into the founding of NuScale Power in 2007. In 2011, we were bought by Fluor Corporation, and from there on, we began really working on the design in a more structured manner. It became more than just a lab experiment. Now, we've been working on it for a number of years. We look at 350 patents, we've got topical reports. You see on there $550 million, about halfway up. We've spent more than that to date. Bringing new nuclear power technologies to the market is not cheap, and it's not easy. Between the time the company was founded and the time we submitted our license was 10 years. That's roughly $600 million of investment. So, looking at the NuScale design, this is a site layout. Some of the interesting aspects of this are we'll have 2 turbine buildings. We have life of plant, dry cast storage within the protected area. And this would be the reactor building. So if you look at the reactor building, this is a cutaway. The NuScale Power reactor consists of 12 50 megawatt power modules, nuclear power modules. Below grade in steel lined concrete container filled with water, over 800 million gallons of water, in an aircraft protected seismic building. This is just an overhead view of it, so you get an idea of where the 12 modules are. We would have fuel storage over here, and this would be our refueling and inspection area. So 12 modules on one side, 12 modules on the other side. So let's look at this from a risk standpoint. So what do I have? I've got my containment building, my reactor pressure vessel, all that and fuel is all below grade and underwater. So by doing that, I've created multiple barriers to the environment. I've got small fuel core, 37 assemblies, 6-foot fuel. So it gives us a core damage frequency of roughly in the 10 to the minus 10th range. So these multiple barriers here of protection give us the ability to move the site boundary from an emergency planning zone basis from 10 miles, where it is today, to the edge of the protected area. Now, this is huge from the standpoint of where can I put this? And we'll talk a little bit about applications as we go along. But think about that from siting perspective, think about it from an operations perspective. I don't have sirens and horns and evacuation plans, so I drive down my operating costs. We look around at what's going on in the US and we see plants prematurely closing, plants at risk. You know, what are ways that we can help drive down that operation cost? This is one of them. Yeah, it moves. So there's an opportunity here to keep making nuclear power competitive. Fukushima. I mean, it's a major event. What happens? So you've lost all off-site power. You have no diesels. So what happens? Well, we know what happened at Fukushima. For us, our plan is for the operators to do absolutely nothing. Absolutely nothing. And this has become a big challenge. What do you train the operators on when the worst event, you don't want them to do anything? So the rods drop, the reactor starts shutting down. You've got decay heat removal system on the outside, it's the blue here, on the outside of your containment vessel. So this is your big concrete dome. So you have decay heat removal. Remember, you're in 8 million gallons of water. So now you start removing that heat through just a lot of water. So decay heat removal in 30 days, you're down to about 0.4 megawatts. Over long term, after 30 days, if you can't find a way to get water there, the amount of heat you're generating is so low, air becomes the ultimate heat sink. I don't need any AC power. I don't need any DC power from batteries. I don't need any additional water. I haven't done anything. That's what small modular reactors can bring. So it's been a long time since I've done engineering and technology work, but I threw in a couple of technology slides anyway. So this is what it looks like. This is a cutaway of the nuclear power module. Fuel down in the bottom, integral helical steam generator, pressurizer up on top. So you saw 2 turbine buildings. The intent of the design is we can eliminate single shaft failures. So you think about a large gigawatt sized plant with a big turbine. You have a problem with the turbine, you're taking 1,000 megawatts off the grid. We're going to have each 50 megawatt module with its own turbine. So 50 megawatt turbines are pretty easy to buy. Put a couple in the warehouse, you have them on skids, you have a problem with the turbine, take one out and slip it in and work on the bad turbine later. So let's see, some of the stuff I covered, yes. So again, just looking at the operations. Natural circulation. This is all natural circulation. Hot water will go outside the steam generator tubes, not inside. So complete, there are no reactor coolant pumps. There are a couple valves. You've got a couple valves up on top. There's a reactor vent valve and a reactor recirculation valve down here. And that's for ECCS. So this is like, better to see over here, and this one on the left. This is like a big thermos. So we have the reactor pressure vessel inside a vacuum inside the containment building. So we're leveraging as much of the world of thermodynamics as we possibly can. Fairly simple. Details on the powertrain. I think for most of the people in this room, powertrain is pretty simple. But here you can see the decay renewable, which actually sits up against here, and some of the configuration. Now, some of the advantages. Steel containment. Small, cylindrical vessel. We end up with 10 times the pressure rate of typical PWR. Water volume is much harder, or much higher, 4 times larger. And we have just this little reactor core down there. And we're only generating 15 megawatts of power. So you get a small source term in the case there's any sort of event. So how do you drive safety as far as you can and drive operating costs down as much as you can? And maximize the capability and the flexibility. So that's what we've tried to do with 12 modules. So, some of the challenges. So, we hear a lot about what's going on around the world, challenges in Finland, challenges here in the US, we have challenges in China, construction. So, some of the lessons learned that I've picked up from the media, license amendments going through that held up some of the work. The impact of ITAC. So we're in a new regulatory regime. And it's got some pluses and minuses. If I had my druthers, if I was running this company, I would not be running a first-of-a-kind reactor through a Part 52 process. I would like the flexibility to be able to make some changes as it went along. Customers like the Part 52 process because there's certainty and finality. So Part 52, the advantage there is your COL, your construction operating license. So I get this license, I get a public hearing at the beginning of it, and when I get my license, I have the license to construct and operate. So one of the big challenges that the NGOs figured out is, well, I'm going to let you build this plant. I'll let you spend all the money you want. I'm going to start litigating as soon as you go back for an operating license. And I'll tie you up because you've got interest on a huge amount of money that you've spent until you go bankrupt. The new process says, you've got your operating license. You have to satisfy a series of inspection, test, analysis, acceptance criteria, ITAC. Now, they can be really challenging. For the EPR, we're talking numbers over 2,000 for ITACs. For SMRs, so far the number we have is 115. 115 inspections to do before the plant is operational. Some of those you do in the supply chain, sometimes you do in construction, sometimes you do in your functional testing. And that's huge. And this is for the first module. So once you get the first module in, you've tested a lot of the systems, that number's only going to go down. So again, how do we drive down costs? How do we make nuclear power competitive? We've got great technology, let's make it competitive. First of a kind, I mean, this is a big challenge. How do you bring something new to the marketplace? So you can't just design for licensing. So there's a safety case to be made. So you design the reactor and you complete all the work to go to the NRC to get licensed. And you submit your safety case, and at the end of the licensing process, they give you a DCA, design certification for your DCA, design certification application. Well, okay, that's fine. But now you have to manufacture it. So you need to work on the design for manufacturing. Then you got to construct it. So you need your design for construction. So the supply chain's got to know how to manufacture and what the challenge are. Your constructor has got to have construction drawings so that they can construct it in the field. And then you have to have all your operating procedures. So when you turn it over, there's got to be design for operation. So you've got to have all the material in place for operation. So some of those things we're working on now. And then there are market pressures to new build. So demand growth. I spend a lot of time visiting utilities. And I ask, well, what's your growth? Oh, 5 years ago they'd say percent and a half. Today, 0.5% or less in demand growth. Well, how are you going to meet that? Well, we think that by upping the capacity factor of our couple of old plants and going through energy efficiency and smart metering and demand response, we'll be able to meet our load for the next several years. They didn't say new generation once. Now, some are putting in new generation because they're forced to. This gets down to the next to the last bullet, renewable portfolio standards. So I'm sitting there as a utility, I'm working in the state, and I've got this state-imposed requirement on my generation. A certain amount of it has to be renewable. And what does renewable mean? I learned for the first time Monday, that hydropower is A, not renewable, and B, is not clean in many states' laws. And I didn't know that until I met with the woman from hydropower. I was absolutely surprised. So at least nuclear is considered clean by most people. Maybe not renewable, but I mean, I could argue that if I went and mined the uranium that was in the ocean, I could fuel the reactors around the world for 1 million years. So how do you define renewable? And is a renewable portfolio standard for what? Are you making it better to build windmills and solar panels? Are you incentivizing them? Or was your intent to create a clean energy portfolio, to force your utility network to make a clean energy portfolio? And if it's going to be clean, then include all the clean energy technologies. And it's been resilient. I went last year there was an attempt made to change the legislation in the state of North Carolina from a renewable portfolio standard to a clean energy standard. And I sat down with President Pro Tem Berger and Senator Brock, who's chairman of the Energy Committee, and they were in full support of it. They started down the process. I got a call from President Pro Tem Berger's aide who said, we're going to drop it. The entire State House was filled by lobbyists. They were everywhere. It was more trouble to try to change it than to just leave it alone. There's a bill that just went through the North Carolina General Assembly that changes the way distributed generation works in the state, primarily for solar. There was an attempt to put a rider on that to add money for an economic development study on small modular reactors in the state of North Carolina. I mean, a huge amount of money, $70,000. $70,000. It was a nightmare. They were bombarded by people to spend $70,000 to do an economic development study. There's a huge resiliency in renewable portfolio standards. Persistent low natural gas. 2007, natural gas was around $14 a million BTU. 2 years ago, it was below 2. It's running around 3 now. Really hard to compete with natural gas at that price. Very hard to compete. Now, my house runs on natural gas, and I get my electricity from natural gas. I mean, 6 cents a kilowatt hour for electricity. I mean, this is wonderful. But from my business standpoint, $3 is extraordinarily difficult to compete against. You can do it, and we'll talk about that, but it is hard to compete against $3 natural gas. And will that always be there? I mean, there's some interesting challenges for natural gas. It's not clean, so when are the NGOs going to start attacking natural gas like they've been attacking coal? Will there ever be a carbon tax? That'll raise the price of natural gas. EPA really hasn't regulated fracking as yet. They're still learning what it is. You start regulating it, the price will go up a little bit. And we're going to export it. We have huge amounts of natural gas. We start exporting natural gas prices in Europe are $8 to $10 a million BTU. In Asia, 14 to 20 a million BTU. What will happen to the price of natural gas in the US? Will it start drifting upwards to be associated with world market prices? As they come down, will ours go up? I mean, there's some interesting things. Not sure where natural gas is going to go. But low natural gas is difficult to compete. So if I look at new build, the challenge for new build, there's some challenges, and they're real. But none of them are insurmountable. So what have we been doing? So we'll spend about $1.1 billion. Of that $1.1 billion, probably, well, I'd say would be about $800 million in the really kind of designing phase. But we're doing other stuff outside of that. So we're spending money on design for manufacturability. People are actually physically making things for us. We're learning what the challenges are in manufacturing these things. U.S. manufacturing, it looks like we'll be able to manufacture all of this in the United States. More pictures of manufacturing, steam generators. This happens to be a large ingot. This happens to be in the UK, Sheffield Forge Masters. They got money from the UK government to do some testing and some prototyping associated with small modular reactors. They approached us. We said we'd be happy to work with them, and for a small amount of money on our part and a good amount of money from the UK government, they've actually made an ingot and machined it. So we'll have gone through some of the manufacturability. So how do we make new build possible, make it successful? Lots and lots and lots of testing. Testing in the US, testing, full-scale testing, scale testing in Oregon State University, testing in Canada, testing in Germany, testing in Italy. There's a lot of testing going on. Some of it for licensing space, other for first-of-a-kind engineering. But we want to make sure that when this goes to market, we're as prepared as we possibly can to be successful. So what is our hope? You make these things in the factory. So this is a stylized NuScale power, nuclear power module. They love those new things at NuScale. manufacturing. So you look at each one of those, and the interesting things is what you're looking at is all the containment domes. So all those big concrete things that you see every time you pass a nuclear power plant, you're looking at a whole row of them there. Those are our nuclear power modules. You make them in the factory. And you deliver them by a truck. Everything but the fuel. And because it's 12 modules, what's that done to my timeline? And what's it done to my cost and revenue stream? I can be adding a 50 megawatt module as I go along. So I start with one, a couple months later I add the second one, then I add the third one. Oh, by the way, when I added the first one, I could close the breaker. Now I'm starting to generate money. And I keep going along in that respect. So I start generating revenue quicker. So I change the cost scheme. Everybody loves a picture taken. This is our chief nuclear officer and our chief operating officer, Dale Atkinson, Tom Bergman, our vice president of licensing, John Hopkins, our CEO, president and CEO. John comes to us from Fluor. John's been absolutely great. Fluor Strategic Business Development, started new companies with Fluor. He's really, really been great for us. And we have a schedule from the NRC. Believe it or not, we have a schedule from the NRC. I know some of you in the room find it hard to believe. And we're actually believing they'll keep the schedule. Yeah, that's even harder to believe, I know. We submitted December 2016. They announced acceptance at the RIC conference in March of 2017. They sent us a formal letter late March 2017. The formal letter gave us a 46-month schedule. So this is the 46-month schedule. As of now, we feel we're ahead of schedule. We're ahead in phase one schedule. And from an RAI, request for additional information standpoint, at this point in time, the Koreans had nearly 6,000 RAIs on their application. So this is about several months in. So we're from January to here, we're about 9 months in the schedule at about 6,000 RAIs. We have 760, and that includes the ones on the topical report. So that's remarkable, but that's a lot of hard work up front. A lot of communication with the NRC, telling them this is what you're going to get, giving it to them, telling them this is what you got. There's a lot of work involved. There's a lot of communication. The good news, that seems to have helped. The bad news is, remember, every time you talk to the NRC, they charge you $260-some an hour. So they said, we want to know something about your reactors. So we said, sure, we'll put together a couple of half-day training courses. So they sent about 90 people to 2 half-day training courses at $260-some an hour. We hope that those people are the ones that they assign to do the review. Okay, it was a good hope at the time. And some of them actually are, but some of them not. But this is what happens when you deal with the NRC. But we communicated a lot, and that's really, really paid off. They're truly beginning to understand our design and the challenges associated with that. And there are a couple of challenges. So for example, we talked about the emergency planning zone. We're gonna go from 10 miles, and we put in a topical report that said, we're gonna do it at the site boundary. Now the actual license associated with that will be in the COL. So the utility will actually submit that. Our topical report is the methodology. They approve the methodology. The utility can then reference the methodology and show that they can have an emergency planning zone at the site boundary. Tennessee Valley Authority just recently submitted their early site permit for the Clinch River site. They put in 2 applications, one at 2 miles and one at 0. And they referenced our topical report. Now, when it comes to it, this is going to be a commissioner's decision. And I don't necessarily always have good words about the commissioners, but the two that have been nominated are really good. So if you get an opportunity to send letters to your congressman in the Senate, encourage them to take these two NRC commissioners and get them through the process. They've gone through committee, the full Senate now have to vote on them. So Annie Caputo came out of Exelon, has a lot of good experience. David Wright, I know very well, Public Utilities Commission chairman out of South Carolina. They would really be helpful to get some extra commissioners. I mean, I remember I listened over the internet to Barron's hearing when he was nominated. So they asked Barron, I think it was Senator Alexander, asked Barron, so you want to be a commissioner at the US NRC. How many times have you visited a nuclear power plant? None. So you want to be a commissioner of the NRC and you've never ever visited a nuclear power plant. That's right. And your experience with nuclear is you wrote policy papers as part of the Energy Committee in the House. Yes. Okay. We need these other people. Be polite. I still need the NRC. They still have our applications. I have to be nice to them. But I mean, we need to get some people on there. When Ostendorf left, he was really the best fresh air that they have. So we have a schedule. They're on schedule. We're optimistic that they'll stay on schedule. So this is the fun part of the design. So what can you do with 12 modules? What do you do with them? I got these 12 things playing around. Why do you want 12 different things? Well, for example, and if you're interested, this is all on the NuScale Power website. All these technical papers are there. So you look at oil refineries. So we can reduce carbon emissions from refineries, 10 module plant, coupled with 250,000 barrels per day from the oil refinery. Hydrogen production, another study on hydrogen production done by Idaho National Lab. Desalinization, Carlsbad, California, and Aquatech. So you've got these modules, you can be producing electricity and you can be doing other things. Integration with wind. I mean, and this is a big one. So we talked about renewable portfolio standards, and you've got all these windmills coming up, and solar farms, and distributed energy. And you've got PURPA law, which means the utilities have got to take this. You must buy. And then you've got net metering laws. So people put these things on their houses, and they send it back on the grid, and they get paid for it. And so they think it's great. So you got all these things going on. But I'm sitting there as the utility, and I'm saying, it's not coming on where I need it. It's coming on when I don't need it. And it's variable. And it can be seriously variable. So how do I maintain the frequency of the grid? How am I going to manage that? So we took one module, 150 megawatt nuclear power module, and analyzed that versus a wind farm in Idaho, Horse Butte Wind Farm, and showed that we can load follow with that wind farm. So now I've got 12 modules. I've shown that one can do it. I've got 12 degrees of freedom. I've got great ramp rates. I've got 100% steam bypass if need be. I've got lots and lots of flexibility. So let's play nice with renewables, but let's get clean energy standards going as well. So as people put in renewables, let's keep the frequencies stable. Let's have that extra power. Let's be able to ramp to meet the times of day, particularly at the end of the day when the sun starts going down and you need this electricity because the variability is off the grid. The other that we've been working on is this mission critical facility. So mission critical facility. So a military base, a national lab, hospitals. Let's create a microgrid using small modular reactor. So, and power that. So we've done an analysis, show that at a 99.999% basis availability, we can guarantee 100 megawatts. And we're looking to see if we can get that to 6 nines. So this is really important to people that can't afford to lose power. So you create a little microgrid for them. I've got 12 modules. And remember, I don't need off-site power. I can black start the grid. I can be the guy that gets that grid back up and going again. I can run in island mode. I can take one module and be running my house loads and have 11 modules in standby. I've got a lot of flexibility with 12 degrees of freedom. And remember, they're all on a single turbine, each on their own turbine. So I've got 12 turbines. So I don't have single shaft issues either. I don't have diesel generators, no batteries. So, again, this is where we are in mission critical. So, what are we doing with it? Are we actually selling anything? It's a great idea. Only great ideas are only great when you actually get to do something with them. So we have a first customer, and it's associated with the Western Initiative for Nuclear. The Western Initiative for Nuclear was put together by the Western Governors Association, who believed that nuclear power, small modular reactor nuclear power, needed to be part of their long-term energy plan. So they put in place a number of policies to support the development of small modular reactors. The first project, as of today, the lead project, is with Utah Associated Municipal Power Systems, UAMPS. Non-nuclear entity, to team with Energy Northwest as the operator, to put a nuclear power plant, small modular reactor, on the Idaho National Laboratory site. So they've already signed a 99-year license agreement, site agreement with Idaho National Lab. Siting studies have been done, so all that stuff is in place. There are others that are interested. The state of Washington is interested. If this goes forward, Energy Northwest is interested in building their own somewhere near the Hanford site. They've already gotten economic development money. Sharon Brown, senator from the Kennewick, Washington area, has been very active. She's gotten money for economic development, for manufacturability studies, roughly $500,000 of study money from the state of Washington to do this. They're very interested, which is a little surprising with all the hydro and the wind they've got from the Columbia Gorge. Yet they think a diverse energy, clean energy, is really important. Boardman, big coal plants are shutting down in Washington state. They're looking ahead. So this is the first project. UAMPS, it's a little challenging here. I give them a lot of credit. So overall, the project is a little behind schedule. UAMPS is a non-nuclear entity that consists of 44 members. So it's a little bit of the nuclear side of herding cats. There's a real challenge for them to get all their members to agree that this is the right thing for them to do. And being non-nuclear, they understood this was going to be a challenge. So this is going to be like drinking out of the fire hose. I think what they've learned, this is really like drinking out of the fire hydrant. They've been really challenged. And to their credit, they come up and they're meeting every single challenge. They struggle a little bit, but they're doing it. They are committed to this project. And this is the schedule. So we're looking at the lower right, we're looking at 2025, 2026 timeframe, they're the first module connected to the grid. There's a lot of stuff to be done, but so far, they're doing it, and they're committed to do it. Now, there are other projects and possibilities. I mean, we look at Tennessee Valley Authority. They submitted their ESP. They're also evaluating small modular reactor technology. So they're evaluating the mPower, they're evaluating the Westinghouse technology, they're evaluating Holtec technology. So far, they're focused on light water reactor technology. But they're evaluating all these to make a technology decision. I was in New Mexico with Governor Martinez and her Energy Committee. State of New Mexico has a lot of nuclear-related industries. They would like to see commercial nuclear power and small modular reactor come into the state. And there are several other utilities who are interested in small modular reactors. Interestingly enough, Monday I met with Governor of Kentucky, and I asked him, can I quote you on this? And he said, absolutely. The quote is, smaller reactors is where it's going. Governor Bevin just overturned the moratorium on nuclear reactors in the state of Kentucky. He and his Secretary of Energy met to talk about how do we get small modular reactors into the state of Kentucky. They are very interested. What can they be doing? There is a lot of interest. Governor Hutchinson of Arkansas is very interested. They're looking at some coal plants shutting down in the late 2020s. How can we get nuclear power to replace those? Governor Bryant from Mississippi, the same thing. So there is a lot of interest on the state level. I had an interesting discussion with Governor McMaster of South Carolina. No, they're not going to build a small modular reactor. But he wanted to know what was going on with the technology and was it available at the time they were trying to make decisions at VC Summer. Answer was no, but he was very interested in the technology. There's domestic markets where this can work. Now, obvious places to build it at a nuclear site. So I was asked by David Fountain, who's the president of Duke Carolinas, well, Sharon Harris was designed for 4 reactors, we only built 1. Can we build 3 more SMRs on there? And I said, you could, but I would not recommend it. You're going to have a very flexible small modular reactor. You don't really need all that much power with the way the market has changed. Leverage that to optimize the operation of your existing plant at that site. Take advantage of the 12 modules. Then there are other sites where they're single plants, Callaway. Let's take advantage of the fact that you've got a lot of flexibility here. There's aging coal. So let's go out in the west. You've got Navajo, Cochise, Bridger, Johnston, Lawrence. These are all coal stations which are scheduled to shut down between 2025 and 2030. The entire infrastructure exists. You've got water, you've got transportation, you've got grid, you've got land, you've got a willing workforce, and you don't have a gas line running to it. Gas pipelines are not easy to site. I mean, Keystone is an example, but we've got the pipeline in northern South Carolina. They've been working on it for years to try to get it moving. Grid infrastructure. The Department of Energy put together grid corridors in the west to try to streamline permitting. And it's still been 10 years to permit new grid. So there are opportunities there where they're looking to shut down aging coal plants. Why would you shut down an old coal plant? For a couple reasons. One, it's not economical to run. Some of these were built in the 1940s and 50s. Two, you're being driven by clean energy standards, renewable portfolio standards in the States. 3, you start looking at where are my shareholders pushing me? What do I need to be doing to satisfy them? And there's litigation associated with that. Sierra Club, Southern Region Defense Council. I mean, they're challenging these coal plants, and as part of the settlement, they agree to shut down a number of coal plants. So there are reasons to shut them down, but there are opportunities to replace that. We need to take advantage of that. So someone said, well, just put a wind farm there. Well, maybe you could. Google, Amazon, Walmart, all looking to go toward clean energy. Google built a wind farm for their data center. So they needed 200 megawatts. So they put in a 200 megawatt wind farm, 20,000 acres. Remember, I only need 35 for 600 acres. 20,000 acres. I'm looking at economic development over my plant of $3 billion. How many people do you need on a wind farm? I mean, a great discussion with Governor Hogan at Maryland. He just authorized offshore wind. Well, they've got all these economic development commitments in there. And I asked Governor Hogan, what are they going to do? Put a bunch of guys in rowboats to go back and forth and check the wind farm? I mean, what is the economic incentive for these? What are they delivering to your state? I'm delivering jobs, real jobs. I can count them. I've got a building. I can count that in the tax base. You can go look at it, touch it, kick it. I've got real economic development. Internationally, there's opportunities around the world. We are approached every now and then. I would say maybe there's 6 or 8 that I would say we should be pursuing. Some in Europe, some in Southeast Asia. There are a couple that are of interest. India, China, they're going to build big reactors. I think let them build big reactors. Russia's going to build their own reactors. Not much you can do to get into the Russian market. UK could be an interesting market. UK will be a market of patience. It's a good market. They really value clean energy. Their process is a little slow. They'll get there. I think it will be a good market. This is an overhead picture of the site. If you drive up there, this is the big Lost River rest stop. You can see the site from there. We have an advisory board. Everybody's got an advisory board. These are, for us, these are entities that are interested in our plant. Some of them more serious than others. Some of them will be plants 3, 4, and 5. A couple are seriously interested in being in the first wave. And there are 2 that we don't have permission to. So we talked about competitiveness. So this is where we are on an LCOE basis. So that's the levelized cost of electricity. We're up about 95. I need to be around 60 for combined cycle gas. That's a big hurdle. So I'm the chief financial officer and I'm running my company and I say, okay, let's put in some new generation. What are we going to do? Oh, let's buy this $95 plant out here. Well, how about that? Then I go to my Public Utilities Commission and say, well, I'm going to build this $95 plant. They said, well, why don't you buy the $57 plant? I mean, this is prudency review. I'm going to make sure you're making wise decisions. So we've got to get down there. This is a study done by NEI. They used EIA, Energy Information Data. So they started with 105. But if I look at this and I talk about production tax credits, I talk about loan guarantees, some accelerated cost recovery, construction work in progress, economic development, tax credits, stabilized production tax credits, power purchase agreements. I can get down to a point where I can be competitive. If I can be competitive on price, I'll win. Because nuclear power can win the intangibles. So, A quick slide on what's needed. This is just things that you've got to be serious. This is not. I mean, I talked to someone from Saudi Arabia. You got United Arab Emirates building a nuclear plant out there. Are you really serious? This is not like buying the latest edition of Rolls-Royce cars. This is a long-term commitment. And these plants will have a design life of 60 years. Probably will run 80. With the construction and the decommissioning, we're probably talking about a 100-year life cycle for this. So you have to make a long-term commitment if you're a country to this. A number of countries will do it. There's some opportunities there. Other things, we talked about a little bit in the previous item costs. What's happening in the state, on the federal level. So on the federal level, we have a new president who's in favor of lots of energy. We have a new Secretary of Energy. Secretary of Energy came out and said, my job is to make nuclear cool again. This is great. So I looked at the first budget. Nuclear is not quite as cool as I thought it was. There's some things that need to be done, and we're working with our congressional reps on things like production tax credits. Energy Policy Act of 2005 had 6,000 megawatts of production tax credits. Vogel and Summer would have used 4,400. That would have left 1,600. It's a couple nuclear power, the full plants for us. If VC Summer doesn't go forward, that's going to be 3,800 megawatts of production tax credits. But you have to be operational in 2020. So we need to get the law changed to get that extended. The loan guarantee program is not funded in the budget. I mean, that's a big deal. The availability of low-cost financing for these projects is important. So those are things that can be done. Internationally, you look at Ex-Im Bank. Ex-Im Bank is a way to finance, to help get U.S. government support for projects overseas. Your competitors are the Chinese, owned by the government, the Russians, owned by the government, the Koreans, supported by the government, Japanese, who leverage Japanese investment banks, which are partially funded by the government. So there's a lot of government support out there. Ex-Im Bank is our ability to compete with those. Ex-Im Bank has a chairman who's acting, a vice chairman is acting, 3 empty chairs. They can't make decisions. We really need to get those things moving forward. So there are things on the federal level that can be done. On the state level, I've been talking to several of the governors. How do we get some of this going forward? How do we get nuclear considered? Let's say we don't change the renewable portfolio standard. What other things can be done? How do we work on statewide production tax credits? How do we work on statewide economic incentives? How do we change the dialogue to bring nuclear into the states? And there's a lot of interest on the state level. I would say there's more interest on the state level for small reactors to be successful than on the national level. So, nuclear power, sales pitch. It's good. It's good. High-paying jobs, economic development, U.S. manufacturing. It's a good thing. That's what I got. Wow. I should have turned the lights on. That put everybody to sleep. So, are there any questions? I'd be happy to take some questions. Yes?
I'm interested more in the specifics of the design of the reactor itself, and I wasn't clear. Did you say there's only primary water, no secondary water?
No, there's secondary water.
Okay.
Secondary water, but we'll run from ours, the fuel is standard U.S. commercial fuel. So it's less than 5 weight percent. Small height, so half height of a typical fuel assembly, but only 37 assemblies. The water will go up and then over, not to the inside, but it's going to go over the top of the steam generator tubes. So we're keeping everything contained that way. So, there it is. So over here on the right. So here's the reactor core. Water heats up, comes up over the steam generator tubes, comes down, cools, and goes back. Natural circulation, no pumps.
Niels, you said that there was no large break, was a cooled accident considered. What is the limiting accident for NuScale design?
I don't know off the top of my head. I don't. I should have that at the top of my fingers, but I don't know off the top of my head. I know that the NRC has tried to impose a large break on us. They've said nozzles are piping. And we've been very fortunate to have strong leadership in the senior projects of the NRC who have gone back to their viewers and said, no, you can't do that. You can't change the regulation in the middle of a review. But I'll find out and I'll get back to you.
So with smaller reactor, the right-way systems, what's the major differences, if you know, between a normal PWR versus SMR?
The systems will be comparable. It's the same fuel. There'll be smaller amounts of it, but it's the same fuel.
Same type of processing of waste, the gasification and all that.
Yep.
Is it the same refueling schedule?
So refueling schedule. So we're looking at 12 modules at essentially a 2-year core. So you could refuel one every 2 months. So when I look at my staffing, I can keep my refueling staff in-house. So we're looking at staffing of about 360 people. That includes the refueling staff and the security. So I'm not bringing in 500 contractors for a refueling outage. So every 2 months I can refuel one of the modules. So if I look at this this is another discussion that the governors are very interested in the Northeast. This is the polar vortex. So the polar vortex, it got so cold that the piles of coal at the coal stations froze. They couldn't get it dug out. It got so cold you had pipelines, gas pipelines freeze. Well, the nuclear power plants continued operating just fine. And with various stages of refueling, I can operate for a long time to keep power going to the grid.
Yes, the schedule you showed for the NRC reviews,
Mm-hmm.
is the project funded to be able to get to those points for the next several years?
Am I going the right way? No, I'm going the wrong way. Yes, we have full funding through FLOR to go through the licensing process. I went the wrong way, didn't I? I couldn't remember. So yes, we're fully funded by FLOR. They've been great. Several hundred millions of dollars they've invested in the project. We're at a run rate of probably 10 to 12 million a month we're spending. And so we're fully funded through the end of the DCA process. They're encouraging us to find a customer that start bringing in some revenue. They are also looking for other investors. So investors in kind of two senses. Investors that bring money, and investors that are willing to do in-kind stuff. And we have some strategic partners that are doing some in-kind work.
Like Enercon, right?
Enercon, we Ares, Ultra. And so there are a few companies that are helping us with providing in-kind activities as their contribution.
Thank you.
Given the southern states have seen the evidence of climate change recently, the hurricanes and obviously elsewhere, is there an opportunity here for the water production to be more of an emergency? Is that viable to have that as an emergency for after a hurricane or whatever it is that water is not available to people?
Yes, the difficulty there is the infrastructure.
Yeah.
So I could generate electricity, but could I get the electricity to a place to generate clean water? Or could I build a facility attached to,
Yeah.
I mean, yeah, you could do that. You could build a facility attached to the power plant to generate electricity, to do that. From a resiliency standpoint, resiliency has become a big word of late. I mean, we're underground, so we're pretty resilient to natural disasters, as most nuclear power plants are.
It brings up a good point. So a lot of the O&M costs that's been dropped from nuclear power plants in the U.S. is driven by all the events such as Fukushima, all these other types of events that really drive enormous costs to those stations. How is the NuScale small modulars being impacted by that, and how have you been able to maybe offset some of those costs?
So on an O&M basis, we're trying to drive capacity factor as high as we can. So we're thinking, can we get to 98% capacity factor using 12 modules? How can we drive down staffing? So you look at the site layout, we're trying to drive out security staffing. Is there a way that we can define it as, okay, all we have to do is hold in place. We don't have to defeat the enemy, we just have to hold in place because the reactor is inherently safe. I can reduce the number of security folks that way. Regulation today would say I need more than 30 operators. The number is 38 operators in the control room. I'll have one control room operating 12 reactors. I'm only gonna have 6 people in the control room. Keep my refueling staff on site. Simpler design, fewer things to maintain. Can I drive down my number of electricians and maintenance people and pipe fitters and a number of those types of activities? Is there a way to leverage the fact that I'm in continuous operation? And we're looking at are there ways to do that. On the more challenging side, and I had this discussion earlier this week with some of the representatives of the state's general assemblies at the Southern State Energy Board. They said, 12 turbines. Your maintenance cost is going to go up. You've got 12 things to maintain. And my argument there is, well, that may be true, but I'm going to have a 50 megawatt turbine, which is pretty standard off the shelf. If a turbine starts having issues, I slide it out, I slide it back in, and I have a crew working on it. Do I really have 12 maintenance crews? I think I can still drive down my operating cost. Regulation is still going to be a little bit of an issue, but if I take the emergency planning zone down to the site boundary, I've driven out a bunch of operating cost.
Is this 12 modules the optimum size for optimum bus bar cost, is it?
From what we've done so far, yes. If I were going to build one, I would not build anything less than 6. So if you look at it, we've tried to break it into half. So you've got 12 modules, one turbine building for 12 modules, one set of systems. So you look at the cooling towers, everything we tried to break in half. So you could build 6 and not build some of the infrastructure. But I wouldn't do less than 6, and 12 would be optimal.
Yes, in the nuclear industry, the trend has always up to now been to build a bigger reactor for economy of scale. You reverse the trend. How do you explain that you reach lower price per kilowatt hour by reversing the trend?
Well, we haven't lowered the price per kilowatt hour, and that's the downside. Big plants are around 5,000, we're around 5,000. So our denominator got smaller. We're down to 600 megawatts, but we also drove the numerator down smaller. So the answer at the end is still 5,000, but we've taken monies out of the top and monies out of the bottom. So that's how we're trying to keep the price, the cost competitive.
Of course, it's still to be seen if you are successful or not
Oh, absolutely.
on the economic side.
Yeah. Yes.
Did I hear you right that, that you will have on site the capacity for dry storage for the life of the plant?
Yes.
So obviously you don't have much faith in the government, taking care of, spending nuclear fuel.
How can I answer that without answering it? I'm not a great lawyer, so I think as I go out and sell it today, that is a question that I'm asked frequently. What do we do with the waste? I needed to provide something, some kind of assurance to say you don't need to build these storage pads out there in the yard. You don't need extra. You know, you've got your 35 acres. And of course, you're going to have more. You're going to have parking, administrative, stuff like that. But you don't need to build these concrete pads to put these big dry gas storage. Yeah. So you were trying to, again, drive down operating costs, keep it simple for the operator. So keep it within the protected area. I am hoping that the current administration, we know it's not a technical issue, it's a political issue with the current administration, find a way to move forward on it. If they do, that's great. But in selling the plant today,
You gotta have the capacity.
you got to be
have
able
it
to
inside
answer the
fence.
question.
I can appreciate that. It's I think, 8 years ago, the Secretary of Energy and Administration just drove a stake right into the industry because they made a promise and then now nothing's being done, essentially.
Yeah, and some places are still collecting money from utility, and others have settled. It's kind of a little bit of a mixed bag, but regardless, we'd like to see the federal government fulfill that obligation that they made to all of us when we built nuclear plants. One more question.
What kind of burn up and fuel cycle length are you looking at? Are you running on one region or multiple regions?
Well, it's 3 regions, but we're not really getting great utilization. We're not driving it to 60,000 megawatt days per ton. That's one of the downside, but we're on 2-year refueling cycles, so that helps a little bit. What we're hoping to be able to use is with 12 reactors, is to be able to drive down total fuel costs, be able to use some of the fuel assemblies that are in the pool that are underutilized to bring those back into other reactors.
You said you were on a 2-year cycle?
2-year cycle.
2-year cycle. So what kind of burn up are you getting?
We're in the low to mid 50s. So not really where I think I'd like to be. Not horrible. That's on a peak pin.
Yeah.
Yeah.
So about 30 average.
Yeah,
If your
30
peak is
you're-
50.
You're talking about 35.
30.
Right.
Yeah. Not where I'd want to be. But I'm trading that off with some other things that I hope will add value. So, thank you, everyone. Thank you for coming.
Thank you, Nils, for joining us, and I really want to thank everyone, especially NAYGN, for organizing this event. I think it was really informative. As a mechanical engineering professor in the energy area, I found it fascinating, very informative on many levels, and I hope you enjoyed it. Thank you, RMU students, for showing up. Quick reminder, the restrooms are across the hall. There's still plenty of snacks available. And there's a little table outside, a little shameless plug for NAYGN. There's some information about the organization and some information about some of our programs that we have here at RMU. So thanks again. Thank you.